So last time we learned how to do left Riemann sums, right Riemann sums, and midpoint Riemann sums. So today we're going to focus on trapezoidal sums, doing our sums with a table that doesn't have equal lengths of rectangles, and what's called the accumulation function or integral.
Still 6.1.
Yep, still 6.1. I'm doing it in a little different order than. Sometimes I feel like the book puts too much in one section and we need some extra time on a section. So we've talked about estimating an integral and how it's basically area under the curve. And we've talked about our rectangular approximations, but we know that they're not super great approximations. It leaves a lot of empty space. So our goal today oh, I forgot to write SWABACT. It's really not that important. Estimate area under the curve. Using trapezoids. That's our main goal today. We're also going to have a few little side goals as we do this. I know. So we do have to remember, how do we find area of a trapezoid? Anyone remember the formula for area of a trapezoid? We have to think all the way back to geometry. Starts with 1/2. Base and height are somewhere, but we also have something a little different.
Base and the top?
When we have a trapezoid, we have a base at the top and
It's
Okay.
B1 plus B2.
B1 plus B2. Now what's different about this than with our rectangles? With our rectangles, the height was to the function. But if we put a trapezoid on to a function, last time we used our quadratic function quite a bit, so let's stick with it. And let's cut this into 0 to 2, 1, cut this into 4 subintervals. So again, we just draw straight up and down lines to make the rectangles, or in this case, trapezoids. But now to make a trapezoid, instead of going straight across, I can just connect my two lines.
Oh my gosh.
See how there's a lot less empty space when we use a trapezoid? It's going to be a better approximation. It's closer to the function itself. So our trapezoids are actually sideways. It's not the way we're used to them being oriented. Our trapezoids are really normally this way. And we have one side that looks like a rectangle instead of, we're used to both sides being slanted. So our bases are actually sideways. and our height is actually the distance along the x-axis. So it looks a little bit weird, and it's different than our rectangles because the base of our rectangle, or the width, we considered on the x-axis, and the height we considered to the function. This time, it's kind of opposite of what we expect. So if we're going to use the area of our trapezoid to estimate this integral, remember we're really estimating integrals, and we will have a way to do this without a picture, but it takes a while to build up to that. So let's estimate this. We said from 0 to 2. So if we split this into 4 subintervals, we'd have 0, 1/2, 1, 1.5, so 3 halves, 2. So we have all those x values. And this time we're going to have to find 2 y values for every area. I can't find this area unless I have both bases. This area unless I have both bases. Okay? So I have to find the area of each and every trapezoid. So let's say I'm going to call them trapezoid 1 plus trapezoid 2 plus trapezoid 3 plus trapezoid 4, just so we can see how these connect to the picture. And let's find the area of each. We know area is 1/2. So we start with that. That's going to be the same for every problem. It's always going to start with 1/2. Then we say base 1. So base 1 is actually the distance from the x-axis to the function on the left side. What's this distance? 0. And again, we're using the function x squared. I said it, but I didn't write it. I should have written it down so you knew what function we were using. So another way to find that, besides looking at the pictures, if we actually plug in 0, we get 0. So we have 0 for base 1 plus, what about base 2? If I'm plugging in 1/2, get this difference, 1/4, so plus 1/4, times the height, which is 1/2. It's at the distance on the x-axis this time. So it's kind of a little bit backwards from our rectangles. So times 1/2 plus, and then we do it again. 1/2, because that's the formula for area of a trapezoid. Base 1, well, I've already found base 1 of my next trapezoid. What's base 1 of my next trapezoid? 1/4. It's the same as the second base of the first trapezoid. So 1/4 plus 1 squared is 1 times, again, 1/2. Plus, so I want you guys to find the last 2 areas. Write out the last 2 areas. So I think I checked everyone. You should have gotten 1/2 times 1 plus 9/4 times 1/2. 1/2 times 9/4 plus 4 times 1/2. And most of you guys just plug this into a calculator, which is okay. What should we?
11/4.
Same thing. You are both correct. Depending on whether you want to put it in fraction form or decimal form. So it's not a lot different than what we did with our rectangles, but it will give us a better approximation than our rectangles did. So I'm going to have you guys try one, and you're going to find oh, that's something different. Okay. Just want to make sure I'm doing it similar to the assignment. So I'm going to have you try one. It'll be just trapezoidal rule. I'm making this one up, so it's probably not going to be super nice looking. That's actually, I'm going to change this -2 to 2, just so we have a different interval than we've been using. We've been using mostly 0 to 2. I'm going to give you about... We are still getting multiple answers, so let's try this out. Again, it's probably something small. There's so many fine little details. And it's all basic stuff, adding, subtracting, squaring. So it's, you know, a negative sign goes wrong one spot. The whole problem's messed up. So we start with 1/2. We have base 1. If we plug in 0, we get 1. Plus base 2, if we plug in 1/2.
Maybe?
It was 2.625.
Never
will
not get that. I did. I got.
Wait, no, I did get
What?
that. Yes,
You got 375?
375.
We should have 1/8 plus 3/2 plus 1. What is that plugged into a calculator? We can do 12, 20, 21 over 8.
1 divided by 8.
Okay, now I got it. You just have to put parentheses around it.
Oh.
Around the 0.5.
I always forget the second one.
Yeah, anytime you square it, it should be parentheses. So it's 21 divided by 8, 2.625?
Yes.
Yes? Okay. So it should have been 2.625 times 1/2 plus 1/2 times 2.625 again. This time we plug in -1. -1 squared, so 1/2 plus 3 plus 1, 4.5. So 9/2 or 4.5? 4.5 times 1/2 again. Plus, I'm going to write it down below because I'm running out of room. 1/2 times 4.5 plus, this time we plug in 6.625.
I got that as well.
Is that what everyone else got?
I got it right. I did it right. I just forgot. Yeah.
Times 1/2 plus 1/2 times 6.625
Let's
plus
go.
9.
Okay, help me keep.
Okay, so what did you guys get for your final answer?
I got a 9.375.
9.375.
But then again, I rounded all
You
the
rounded.
numbers up.
And
So
then
I got 9.3.
Almost done.
So
9.375. I just plugged it into the standard one. I just plugged it into
Okay.
Means anything.
So, what if, so on all these problems, we've been given a function and we're cutting it into equal subintervals. What if we don't have equal subintervals? What if instead, so that's kind of example 1, I don't think I ever labeled it as example 1, but what if instead we have a table? And there's no way to do equal subintervals. Okay, so this time let's do a left Riemann sum. So if we need to, we can draw a graph just to give us a general idea of how this is going to work. And this one especially, where we have a negative y value, it's going to throw us off a little bit. So at 0, we have a height of 0. 4, we have a height of -1. 5 is back to 0. 7 is +1. And 8 is back to 0. So this time we do not have equal subintervals. This time I couldn't use a function, I couldn't just plug in my values. It helps us to actually draw the rectangles themselves. So when I have a table, we don't want to connect these dots. We don't know exactly what the function looks like. But we can still draw our rectangles. We have a lot of zeros, so we only have 2 spots where we actually draw a line to the x-axis. And then we're still taking the rectangles between 2 points. So if I have my point at 0, 0, and my point at 4, -1, where should I draw my rectangle from? If we're doing a left Riemann sum on this one. Should I draw it from 0, 0, or should I draw it from
It should be
4, -1? 0,
0,
0. And if I draw the height of my rectangle from there to this line, it's all along the x-axis. My rectangle is a line. Then we do the next one. So this next one, the left side of my rectangle is my point for -1. So we draw our rectangle that way. Then we go between the next 2 points. On the next 2 points, the left side is at 0 again. And on the next one, the left side is at 7, 1. So a lot of these, looking at the picture, we can see easily they have an area of 0. Well, let's actually write out the formula like we would if they didn't have an area of 0. So if I'm doing LRAM, we want the area of the first rectangle. What's the width of my rectangle? 4. Times the height. The height is 0. Plus, then we go to the next one. What's the width of my next rectangle? 1. What's the height? -1. This time we're going down. Plus, what's my next width? 2 times 0. Plus, what's my next width? 1 times a height of 1. So we would simplify this down. We get 0 minus 1 plus 0 plus 1. And an overall net change is 0. Remember, we're thinking of this as deciding position. So this object didn't change position for a while, went backwards in position 1 step, and then moved forward in position 1 step. Approximately. This is an approximation of position. Now, let's look at our table and see if we could have done it without the picture. So table-wise, how did we find all of these widths? Looking at my table, how do I find the width on the table? If I'm looking, is our width the x direction or the y direction first?
It's the
X direction. So how could I find my width between my first 2 points?
Look between the first and the second one.
Subtraction. 4 minus 0
Oh.
gave me my first width of 4. What about my next one?
It's 5 minus 4.
5 minus 4, which is 1. 7 minus 5, which is 2. 8 minus 7, which is 1. So we can find all our widths by subtracting. What heights did we use? We used which y values in particular, though?
Oh, the
Which-
second Y value.
Which y values did I start with? Which one did I start with?
Start with the first and did it the other.
I started with the first. Which one did I end with?
The second to last.
The second to last.
Because it's the Loram.
Because it's a left Riemann sum. If it's a left Riemann sum, I use all my left heights. I don't use the very most right one because we're going from the left, not from the right. So if I was doing a right Riemann sum, which point should I use for my RRAM?
0, 1, 0.
The ones on the right. So I start at -1 and move on. So for RRAM, I would go still the same width, 4 times -1 plus 1. I'm looking at the width. I was looking at a value instead of the width. 1 times 0 plus 2 times 1 plus 1 times 0. So all my widths were the same. The widths didn't change. But the heights did because now I'm using different y values. So my widths didn't change, my heights did. We simplify this, we get -4 plus 2, which is -2. So we know our actual integral would be somewhere in between. We have a table, so we have no way of knowing exactly what it would be. Now, what if I wanted to do a midpoint sum on this one? Josh says, I don't know if you could. We couldn't. If I had my table with, like if I did 0, 2, 4, 6, 8, and then I did midpoints, so if I went from 0 to 4 and did halfway in between and got the 2, I'd have to have a very specific type of table in order to do a midpoint sum. So we can't do a midpoint sum, but we could still do a trapezoidal sum. So I can't do a midpoint sum, but I can do a trapezoidal. Running out of room. So I'm going to move this so that we can still see the graph. Ah, come on. I want the whole thing. So we can still see the table and the graph when we do trapezoidal. Because otherwise, I have to redraw the whole table. So trapezoidal. We know always starts with 1/2. And then we do base 1 plus base 2. So trapezoidal is going to look a little bit different. Trapezoidal would end up connecting and looking like a whole bunch of triangles on this one. So our first trapezoid, what are the bases on either side? What are the y values on either side of our first trapezoid? What's the y value on the left side? 0. What's the y value on the right side? -1. So we're using both values for base 1 and base 2. Then we group the next 2. Then we group the next 2. Okay. And trapezoidal, we do use all the y values. Left, we only use the left ones. Right, we only use the right ones. Trapezoidal, we're going to use all of them. So 0 plus -1 times, this time our height is different. What's our height? It's 4. It was the same as our width on our rectangle. Remember, the trapezoids actually, the width is associated with the height of the trapezoid. So the width of the rectangle is the same as the height of the trapezoid. Plus, then we do 1/2 times the next group, -1 plus 0 times 1. Plus 1/2 times 0 plus 1 times 2. My width was 2, which is the height of my trapezoid. Plus 1/2 times 1 plus 0 times 1. If we simplify all of this, you would get -2 minus 1/2 plus 1 plus 1/2. Okay. Which is -1. And your trapezoidal rule should always be a better approximation. So it's going to be between your right and your left. This is a better approximation than we had before. We don't know again if it's the exact because we don't know what the function is. I was going to talk about one more thing, but I think I'll save that for next time. I don't want to go all the way till the end of till when the bell is going to ring.